This example tries to highlight how we can use Bayes' theorem to compute updated or posterior probabilities after having new information given the prior probabilities. So in this example, imagine we're talking about liver cancer screening, just as an imaginary example based on blood test. Suppose that there is 0.0001, so it's about 1/10,000th of probability that a patient has liver cancer before testing. So it's 1/100th of a percent. That's across all ages for population of patients. And suppose that it's given this information that false positive test for the specific test that is being used is 50%. So there's a 50% chance that the test would come out saying you have the liver cancer, but actually you don't have. And also suppose that the false negative test is 25%. So it means, suppose that the test comes back saying that you don't have cancer while you have actually cancer. The chance for that is 25%. Part A, we want to compute what is the probability that a patient has liver cancer if the blood test indicator comes back actually positive. I'll talk about this interesting histogram as well later. Basically, this histogram is trying to show you that when age of population or specific patient is less than 50, then the chance of having cancer is substantially lower. And as soon as we pass the threshold of 50 on average, statistically speaking, then the chance of having cancer exponentially grows to the extent that as soon as we get to 60 and 60 plus, out of a population of 100,000, 40 on average will have liver cancer. So you're talking about 0.4 of probability having the liver cancer. So you can see that this histogram indicate beyond 50 and especially 60, the chance of having liver cancer exponentially grows. For now, let's forget about the age. And in part A and also part B, we are just dealing with general population. Okay, so the best thing to do is computing. What are we trying to figure out in part A? What is the probability of a patient having liver cancer if the blood test indicator comes back positive? Let's say, let's just say that blood test positive, that's an event. So that in that event, let's name it as blood test positive. And for the event of blood test negative, let's just name it as the event of blood test negative. And of course, having liver cancer, let's just event of, so the event of having cancer, let's say having liver cancer, let's refer to it as LC. And event of not having cancer in this example, let's refer to it as NC. And of course, we know NC is naturally is a complement of LC. So the probability of not having cancer obviously is 1 minus probability of having cancer. So having said that, let's deal with A. In part A, we are saying what is the probability of patient having liver cancer while the test comes back positive. So in part A, we want to compute probability of having liver cancer given that test is positive, blood test positive. That's what we want to compute. The best thing to do is just using conditional probability formula, which just simply says compute this, the joint probability of having liver cancer and blood test positive, divide by the probability of blood test positive. Okay, we don't have this information. The only thing we know here is the false negative probability, false positive probability, and also the general probability of having liver cancer. So what I'm going to do is I'm going to rewrite it in a form that I can use this information, because this false positive, so this general probability is what we refer to as probability of having liver cancer. Okay, this false positive is the probability of the blood test says it's positive while the patient doesn't have cancer, so not having cancer. That's this false positive. The false negative is the probability of the blood test turns out to be negative while the patient really has liver cancer, LC. So these are the three values that are given to us. So in order to compute this, I need to reform this conditional probability in the form of just using multiplication law. I'm going to have probability of having blood test positive given the patient has liver cancer times the patient has liver cancer, and divide by, of course, this probability can be written as probability of having blood test positive and have while the patient has liver cancer, plus the probability of negative positive blood test and not having liver cancer, which means not having liver cancer. And I'm going to rewrite these two in the form of, in the denominator, blood test positive given liver cancer times probability of liver cancer. And for second one, I'm going to rewrite it in the form of probability of having blood test positive while there is no liver cancer times the probability of not having liver cancer. Okay, so the only thing I need to do is just substituting these values. So in numerator, this is easy to compute because I have the false negative. So when somebody has liver cancer, I know the blood test reporting negative is 25%. So this event is just complement of that. So this is 1 minus 25. And of course, probability of having liver cancer is what is given to us here. So it's just 0.0001. Okay, so I'm going to just have 0.75, which is 1 minus 0.25 times the probability of having liver cancer. Okay, and let's say denominator, same thing repeats. Okay, and this conditional probability here is what we have actually as false positive. The probability of blood test turns out positive while the patient doesn't have the liver cancer. So that one is already 0.5. And probability of not having liver cancer is what we just briefly talked about here, which is 1 minus 0.001. So this number is obviously 0.9999. So 0.9999. All right, it's not difficult to compute this. So maybe the best thing to just quickly compute this is just saying this number is 3/4, 3/4, and is 1/2 or 2/4, and then we get 2 to the, we get And maybe we multiply both numerator and denominator by 10,000. So we get 3 over 3 plus 2 times 9999. So that's what we get. What I did is just multiply both numerator and denominator by 10,000 and also by 4 so that I get rid of the fractions. And when you compute this, you easily see the outcome is 3 plus 2 times 999, and then 1 over that times 3. So you can see that the probability becomes, the posterior probability in this case is roughly 1.5 e to the minus 4. So what you're saying is your probability now is this, roughly. So it's interesting. What is this trying to tell you is, without the knowledge of the blood test positive, you would say the probability of the general population, a patient from the general population would have cancer is just 1 e to the minus 4 or 1/10,000. Now that probability have increased by 1.5x just by knowing the information that the blood tests turn out positive. So this is what we refer to as posterior probability, the updated probability after we receive the information about the blood test, basically. So now another posterior probability that we're interested in is the part B, which says, what is the probability that the patient has liver cancer if the blood test indicator comes back negative? So you would say probability of having liver cancer if the blood test is negative. It's very similar to what we did here. So it would be, I'm going to just directly write the Bayes theorem formula, which is this. So all this, let me use a different color to highlight. Okay, so this is the Bayes theorem formula. So I'm going to use that. So it's going to be probability of blood test negative given there's liver cancer, and probability of liver cancer, probability of blood test negative given liver cancer, probability of liver cancer, plus probability of blood test negative given no cancer, probability of no cancer, no liver cancer, basically. So in this case would be exactly same situation. Now, this probability here, as you can see, is the false negative. So it's already given to us. That is 0.25 or 25%. And probability of liver cancer, it's already computed. It's 10 to the negative 4. Repeated below. Okay, 10 to the negative 4 plus this one here. We already know that the false positive is this one, which is the probability of blood test positive given no cancer. So now we are interested in blood test negative given no cancer. This is equal to 1 minus probability of blood test positive given no cancer. So we have this number. This is 1 minus 0.5, which happened to be again 0.5. So 50%. So I would say repeat 0.5, and then probability of not having cancer, same as before that we computed, is 0.999. So if you recompute this whole thing, you get 1 over, again, I multiply both numerator denominator by 10,000 and also by 4. So I get 1 over 1 plus 2 times 9999. And we can compute this number similar to what we did. So let's do that. You're talking about 2 times 9999 plus 1, and then inverse That's what we get. We get 5e to the negative 5. So what you are now computing is this. Interesting. So the second posterior probability, which is the probability that is asked for in part B, the probability of patient having cancer when the blood test comes back negative. Now you can see that the chance of having cancer is reduced by a factor of 2 just by knowing that the blood test is negative. This is another posterior probability. So part C is just asking you to repeat this whole thing by, let me just select another color. Part C is asking you to repeat part A and B now for old patients. So when you look at the old population, this range, you can see that for old population, the chances are increasing exponentially to about 4 times. So now we just need to compute basically these numbers again. And if you do that, so part C, recomputing or recalculating parts A and B using probability of having cancer this time 0.0004, which is 4 10 to the minus 4. Okay, if you do that, so for P of having cancer given positive blood test will turn out to be, since the false positive and false negative probability hasn't changed, I'm going to just rewrite this portion. So it will be same thing, except that I would basically replace this with 4 times number, the same thing for this probability, and this, instead of being 0.9999, will be 0.9996. If you do that, this portion, this number becomes effectively 3 times 4 plus 2 times 9996. That is what it becomes. And if we compute that, it will be 2 times 9996 plus 12 and 1 over x times 12. So you can see now the probability increased to 6 10 to the minus 4, which means you're talking about this probability. Roughly. And for the other posterior probability of having cancer given blood test negative, the same thing. You repeat the same thing that we did in part B now with the new 4 times higher prior probability of having cancer. So if you do that, I'm going to just replace this with 4 times number, replace this with 4 times number, and replace 0.9999 with 0.9996. That's what's going to be the case. If you do that, then you end up with 4 over 4 plus 2 times 9996, which if you compute will be 2 times 9996 plus 4, 1 over x times 4. So now you're dealing with 2 10 to the minus 4. So for these posterior probabilities, now you can see that when there is a negative blood test for old people, the chance of the negative blood test indicates that the chance of having liver cancer is reduced by a factor of 2. And having a blood test positive increases the chance of having the liver cancer by 1.5x from prior probability of 0.0004 to this posterior probability, which is 1.5 times higher. So part D, what can we learn or infer from these test results from parts A, B, C? I would just say we can see when we are dealing with aged population, the impact of results of tests are magnified. So, in this case, also because the false positive test and false positive rate of the test and false negative rate of the test is not that bad, the impact of it in terms of magnifying the chances or reducing the chances of having liver cancer in overall population is not that bad. So maybe if such a test really exists with this performance in terms of false positive and false negative rate, maybe beyond some age, say maybe 50, it can be recommended as an annual practice or preventive method to really examine the chance of patient having a cancer or not. So that is what we learned from this.